Welcome, students. Topic to be covered is stability of dyene. We have discussed about types of dienes and what are dienes, their properties, their method of preparations, and their mechanism of reactions. To start with, we just have to remember that there are three types of dienes. The number one is conjugated diene. The second one is non-conjugated diene. It is also called as isolated diene. The third one is cumulated diene. I advise you to refer to a previous topic which where detail we have discussed in detail about topics of introduction of dynes, type of dynes, and their method of preparations, their properties, and all. To begin with, we have to focus on one thing, that we are going to determine the stability of dyne with the help of heat of hydrogenation value, and it is denoted by delta H, and it has negative charge because heat is released. Because it is released, it will have a negative charge. So the value what we are going to get as delta H, and we are going to get some value as negative with kilocalories per mole as its unit, will help us in deciding out of these three dienes, that is conjugated, non-conjugated, and cumulated, which is supposed to be more stable. We are going to take the same hydrocarbon. That means if I'm going to take 5 carbons for conjugated diene, I'll take same 5 for non-conjugated, same 5 for cumulated. And we'll land up with some values for each one of the conjugated and non-conjugated and cumulated diene. And that will help us in deciding which of these three, in which one is more stable out of these three. Before going into the reaction part, only thing we have to remember, very simple thing, is stability of a compound is inversely proportional to energy. That means here our energy here is delta H. Delta H is heat of hydrogenation. If stability has to increase, or if the value of the conjugated diene or non-conjugated diene or cumulative diene has to be stable, energy should be less. So if you have three values, that is minus 30, minus 45, and minus 60, out of these three values of delta H we are going to get, minus 30 will be more stable, minus 45 will be the second one, and minus 60 will be the third one. There is simple logic what we have to remember here. And we are going to discuss the same analogy in our reaction part. So this part is important to understand this thing. The second thing here is, what is delta H? Delta H is the heat released when hydrogen is added to the diene. And this addition of hydrogen is happening in the presence of a catalyst. Addition of hydrogen in the presence of catalyst is catalytic hydrogenation. So catalytic hydrogenation of dienes will give us delta H value, which will be a negative value. This will help us in deciding which is more stable out of these three dienes which we have. This is the only concept which you have to remember for stability of dienes. It is very simple. We have three types of dienes. Out of these three types of dienes, we are going to decide which one is more stable based on heat of hydrogenation. What is heat of hydrogenation? Heat released when hydrogen is added to the diene. And remember here, because if you have one double bond, you require two hydrogens to break the bond. If you have two double bonds, in this case we have two double bonds because it is diene, so we require four hydrogens. You have to remember here, dienes are those compounds which contain two double bonds, and there are three types of double. So this is very simple. Next is we are going to take an example here where 1, 2, 3, 4, and 5 double bond, single bond, double bond, single bond. So when you have double bond, single bond, double bond, single bond, this type of diene is called as conjugated diene. Why it is called as conjugated? Because here you have double bond and single bond, double bond, single bond. Alternating double bond, single bond is called as conjugated, and that particular diene is called as conjugated diene. And if I number it, it is 1, 2, 3, 4, 5. First position, third position. It is 1 comma 3 pentadiene. I'll remove the numbers from here. It is 1 comma 3 pentadiene. This hydrogen here will be 2 because it has only 2 bonds. This carbon has 3 bonds, so only one hydrogen. This carbon also has only one hydrogen space. This carbon also have only one hydrogen space, and this has three hydrogen space because it has only one valency saturated. So this particular CH bond, so this, sorry, rewrite it properly. CH double bond, sorry, single bond CH3. So we have this compound that is 1 comma 3 pentadiene. This 1 comma 3 pentadiene undergoes hydrogenation in the presence of a catalyst. It can be platinum, it can be palladium, it can be any metal. So this is catalytic hydrogenation. Because this particular compound, that is conjugated diene, has two double bonds, we'll have to take two hydrogens, that is 2H2. But we'll start with one hydrogen here. If we are going to go for this particular positions where there is double bond, so double bond is present between these two carbons. So one hydrogen from here will go to here, and another hydrogen will go to this particular carbon, and this results in breaking of this particular bond. So this bond will be now changing to from double bond to single bond. So what will I write here is from CH2 to this particular carbon, it will change to CH3. From double bond, it will change to single bond. From CH here, it will change to CH2. Single bond CH, double bond CH, single bond CH3. But remember here, we have just now done the addition of hydrogen to only one possible position. Now, I'll rewrite this one. It was CH2 double bond CH, single bond, right? So we have another double bond here which we have to target. So instead of writing H2, I have to write here 2H2. So from this, one hydrogen will go here to this carbon, the another hydrogen will go to this carbon. This results in breaking of this particular bond. So what happens here is this bond, here I am writing CH, this will become single bond. So this one, this particular carbon CH will change to CH2, double bond in single bond, CH will change to CH2, single bond, CH3. So this is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. We get a pentane, it is an alkane, and we get a delta H value. The delta H value here is minus 54.1 kilocalories per mole. This is the heat of hydrogenation, that is heat released when hydrogens were added. We are going to add two hydrogen because we have two double bonds here. Two double bonds are broken and hydrogens are added to these two positions here and these two positions here. So this is the heat of hydrogenation which is released, that is 54.1 kilocalories. This is for conjugated dye. The next one I'm going to discuss is isolated diene, which is also called as or non-conjugated diene. We're going to take same 5 carbons, 1, 2, 3, 4, and 5. If you have double bond here, then double bond will be here. There is no alternating double bond, single bond, single bond, and double bond. So this is not conjugated. That is why it is called as non-conjugated diene or isolated diene. The same thing here. I'll write hydrogens here. It having two bonds here, so it will have two hydrogens remaining. Three bonds to this particular carbon, so only one hydrogen. Here it has only two bonds, so it will be CH2. This particular carbon has three bonds, so only CH, and this carbon has two bonds, so CH2. This is going to undergo, sorry, plus hydrogen. So as we know, it is having two double bonds, so 2H2 in the presence of platinum catalyst. First thing is we are going to target this two carbons, double bond will break and this CH2 will change to CH3 and this CH will change to CH2. So I'll write here CH3, double bond change to single bond, CH changes to CH2. Then followed by this position where there will be no change, so single bond CH2. Then going to this particular two positions where double bond will be removed, CH will change to CH2, CH2 will change to CH3 due to addition of hydrogen. So single bond CH2, single bond CH3. So we have another alkane, that is pentane, due to addition of hydrogen, and it is in the presence of catalyst. It is called as catalytic hydrogenation. We get a delta H value here as well, and we have negative value because energy is released, and we have value of 60.2 kilocalories per mole. Previously we got for conjugated 54.1, here we got 60 point. So in this two, conjugated and non-conjugated, conjugated is more stable because it has lesser delta H value. So lesser delta H value, more the stable diene. In this case, conjugated diene is more stable than isolated or non-conjugated diene. The final one is cumulated diene. The same 5 carbons we are going to take 1, 2, 3, 4, and 5. This one is little uh, confusing because we have two double bond adjacent, so it is a little bit mm, tricky compared to the conjugated and isolated one. So after writing this cumulated diene, we can now write down the hydrogens. This will accommodate two hydrogens. This cannot accommodate anything because it has 4 bonds saturations. The third carbon here will have only one hydrogen. This will have CH2. This will have CH3. This cumulated diene, and the position is at first and second position, plus two hydrogens. I can also shift double bond in my notes which I am going to send. So it's better I'll write double bond here only, so there will be no confusion, right? So it will be now at second and third position. So 2 comma 3 pentadiene. So is the IUPAC name of this particular compound. I'll remove the numbering for any confusion. And this reaction is happening in the presence of platinum catalyst. So here at we have this two carbons first. So I'll write down first thing. Yeah, here it will be CH3 then. Sorry, the hydrogen will also change. This will be CH3 because it has only one bond. This then will be CH. Okay, I'll rewrite this one to omit any confusion. 5 carbons, 1, 2, 3, 4, 5. Here it will be CH3. This one will hold only one hydrogen. Here it will be no hydrogens. Here it will be CH, CH3. So we're going to add up two hydrogens first here. So this bond will be breaking. I'm going to write here CH3 as it is, followed by CH2. Double bond will change to single bond. C will change to CH. So after this position is or double bond is removed, we have double bond between just two carbons. Then after addition of hydrogen, this C has changed to CH. Now once again on addition, the CH will change to CH2. Double bond will be removed, single bond, CH will change to CH2, single bond, CH3. Once again we got a pentane here with a delta H value which is equal to minus 70.5 kilocalories per mole. So we have three delta H value, that is for conjugated I have minus 54.1. For non-conjugated, we have minus 60.2 kilocalories per mole, and for cumulated, we have a value of around minus 70.5 kilocalories per mole. So out of this three, the conjugated diene has the least delta H value, followed by non-conjugated, followed by cumulated. So the order of stability will be conjugated diene, followed by non-conjugated diene, followed by cumulated diene is the stability order of dienes. I think it is very simple for you to understand now if you know the basic analogy which we have followed in the beginning. But what makes this conjugated diene more stable actually is that conjugated diene has double bond which undergo electron delocalization. What is electron delocalization? Electron delocalization is nothing but movement. It moves. Movement of pi electrons from one position to another. For example, you have, giving you one example of butadiene. There is no need to specify hydrogens here, but what happens here is double bond here will go from here to here, and then this will go from here to here. Then what happens here is, because the double bond is shared between these two carbons, now we have to write here carbon carbon double bond C. Here double bond will be shifting, then this carbon will lose this double bond, but double bond is shifting to this particular carbon, that means it will get negative charge. Because this carbon is losing this bond from here, it will get positive charge. In the same way, we have another way of representing this, that is, once again I'll write down this one, where we have 1, 2, 3 and 4. The another way of representing this is, this will shift here to this position and this will shift here. I'll write all the 4 carbon first, 1, 2, 3, 4. Because it is shifting here, I'll get double bond here. Because this carbon is losing, it will get positive charge. And because this carbon is gaining, it will get negative charge. This is nothing but delocalization of pi electron. These are resonance contribution of pi electron due to pi electron delocalization. And this results in a hybrid where carbon, I'm writing 4 carbons as it is. See here, all the positions here, 1, 2 and 3 has pi electron. So it will be represented as broken lines. That means pi electron is moving from one position to the another. It is called pi electron cloud. When I'm writing or representing in broken lines, it is called as pi electron cloud. And compound what we are actually getting after delocalization of pi electrons is called as resonance hybrid. And this resonance hybrid, which is actually only seen in conjugated type of diene, is due to pi electron delocalization, is resulting in making your compound more stable. So electron delocalization is actually making your compound more stable. This is what you have to remember. So here I'll stop this topic. We'll continue in our next class. Thank you.